So myself, I am Dr. Shankaraiah, Department of Associate Professor in Department of Physics. So in the last presentation, I have discussed about population inversion condition and metastable state. So in this presentation, I will discuss about lasing action. So all these topics are in module 3 of applied physics, which is lasers and fiber optics. So I am discussing the topics in lasers. So in the presentation, in the last presentation, I have started discussing about this. So we have discussed a few points in lasing action, starting with what is this optical resonator or optical cavity and what is active medium, right? So lasing action is the process that occur in a system, in our lasing system, that will give us in a laser, okay, that will give us the output laser beam. So what happens in this lasing action or in a laser medium, the laser system, that will give us as a laser beam, okay. So to understand this lasing action, we need optical cavity or optical resonator. So this optical resonator is also called as optical cavity, okay. So optical resonator is also called as optical cavity, and so optical cavity is represented here by this dashed line. So this one completely, this one is, this is a optical cavity or optical resonator. So optical resonator contains two mirrors. One of them is 100% reflecting and one of them is partially reflecting. So partially reflecting mirror is always in the front and 100% reflecting mirror is always at the back. And in between these two mirrors, you have active medium. Okay, and this active medium is connected to a pump. Active medium is connected to a pump. Okay, so the reason for placing the partially reflecting mirror in the front is that we need to have the laser beam coming out from the front. This 100% reflecting mirror is, it reflects whatever photons that come here to this mirror, it reflect 100%. So that is why we are keeping this as back, so that whatever photons that are coming to this mirror, this will reflect back into the active medium. So the 5 steps that are involved in a laser system that will give us a laser beam as output are pumping. Step 1 is a pumping. Step 2 is population inversion, and step 3 is spontaneous emission. Step 4 is amplification, and step 5 is oscillations. So the 5 steps that are involved in a lasing action are pumping. First one is pumping, population inversion, spontaneous emission, amplification, oscillations. Okay, so we will discuss in detail why do we need all these steps, or what happens in pumping, and what happens this population inversion, what happens in spontaneous emission, or what happens in amplification, and what happens in oscillations. So we will discuss in detail all these 5 steps to understand how do we get laser beam or a laser as output. Okay. Okay, before trying to understand all these 5 steps, we need to understand why do we need this optical cavity. Okay, without optical cavity, can we get the laser beam? We will see. Can we get or not? The primary function of the optical resonator is to provide positive feedback of photons into the medium so that stimulated emission is sustained and laser acts as a generator of light. So the answer is no. If you do not have optical resonator, you are not going to get the positive feedback of photons into this medium. If you do not have this positive feedback of photons, you are not going to get this stimulated emission. Okay, it will not sustain for a long time, and you are not going to get the laser as a light output light. Okay, so optical resonator is very important because optical resonator is nothing but 2 mirrors. So what do you mean by optical resonator? Optical resonator is nothing but there are 2 mirrors. There is one 100% reflecting mirror. There is one partially reflecting mirror. So this is partially reflecting and this is 100% reflecting. And these 2 mirrors, in between there is a active medium, and that is connected to a pump. And if you do not have these mirrors, whatever photons that are emitted in the active medium, those photons are going to emit. So you are not, they are going to lose, you are going to lose the photons from the front mirror and back mirror. So you are not going to get a laser beam as a output. So you do not want to lose the photons that are emitted in the active medium. What you want is, you want to collect, or you want to see the collection of photons that are emitted as a laser beam. To get that collection of the photons as a output, you need to have this optical resonator. This optical resonator, whenever a photon is emitted in the active medium, these photons are going to get back. So once it goes to the 100% reflecting mirror, this mirror is going to reflect the photon, and these photons will come back into the active medium, and it will help the system to get more stimulated emission, and hence there will be more photons. Those photons, once there are more number of photons that are going to come out as a laser beam. Okay, so the primary function of these optical resonator is to provide positive feedback. That means whenever photon is emitted, that photon, these mirrors are going to send them into the medium again. So that is why we are saying positive feedback of photons into the medium. Once you have this positive feedback of the photons into the medium through these mirrors, those photons are used for the sustaining of this stimulated emission. Okay, once we have this stimulated emission sustained for a long time, you are going to see the generation of light. So the five steps that we have discussed in the previous slide. What are the five steps? First, starting with the five steps, starting with the first one is population. No, sorry. What is the first one? First one is pumping. The first step is pumping. Okay. So how do we understand pumping? So first, we know that whenever you take a material, all the atoms will be in the ground state. All the atoms will be in the ground state E1, and there will be very few atoms in the excited state. Here we have created the metastable state somehow by adding impurity atoms. So higher energy level is a metastable state. Okay. So we do not want to have this normal state or equilibrium state, because we want the atom should be in the ground state so that we achieve population inversion. So first we are going to send all these atoms in the excited. So this state is actually called as normal state, right? So this state is actually called as normal state. Okay, but we do not want to have this normal state. We want to have an inverted state, right? So how are we going to get this inverted state? We are going to pump, we are going to supply energy. So this is E1 and this is E2. All the atoms are in the ground state. For example, only one or two few atoms in the excited state. Now I am going to supply energy in the form of light. For example, when I supply light to these atoms in the ground state, these atoms are going to absorb these photons, or slowly they are going to get excited to the higher energy level. Okay, so that is the reason why the first step is pumping. Okay, so once you do this, supply the energy, which is called as pumping, the atoms which are in the excited state, they will go, which are in the ground state, they will go to the excited state. Okay, so fine. So the first step is pumping. So you can see all these figures where you are seeing the atoms are emitting. The atoms are emitting optical pumping. This is a non-excited state, which all the atoms are in the ground state. Then we are saying if there is excited state, the first, then we are supplying energy, optical pumping. First, this is a normal excited state, which is all the atoms in the ground state. Then, so you can see this active medium is containing host material and active centers. And all the atoms are in the ground state, non-excited state. Then we are supplying energy in the form of light. So that is called as optical pumping. Once we supply energy in the form of light, which is called optical pumping, now atoms are going to get excited to the metastable state. Okay, then there will be spontaneous emission and stimulated emission. You will see photons are emitted. These photons are getting feedback, positive feedback, because of the partial 100%. This is 100% reflecting mirror, and this is partially reflecting mirror. Because of the presence of these mirrors, these photons are getting back. See, once the photons are going here, they are coming back into the system. They, from even when they go here also, they are going to get back. Some of them, very few will lose, but most of them are going to get back to the into the active medium, and these photons are going to used for the sustaining of this stimulated emission. And there are, once there are many coherent photons that are emitted, you will see there is a amplification of light. Okay, amplification of light, and then finally you will see once there is a sufficient energy up to emit, then you will see there will be a laser output. So this is a systematic or pictorial representation of how we are going to get the laser beam as output, or how these 5 steps are um, done in the system. Okay, so we will discuss in detail one by one. So this is a pictorial representation of all those 5 steps. So I think from this itself it is very clear what is happening in the system. Okay, to revise once again, first you have a non-excited state. That means you have a normal state. All the atoms are in the ground state. All the atoms are in the ground state, which is a normal state. And then this active medium, which contains host material plus active centers. Active centers are nothing but the impurity atoms or defects. Okay. Now, when we supply energy in the form of light, pumping. First step is pumping. So when we supply energy in the form of light, these atoms are going to get excited to the metastable state E2, and then when the atoms are in the metastable state, then N2 will be greater than N1. You achieve population inversion, and then there will be spontaneous emission, and hence followed by a stimulated emission. Whenever there is a stimulated emission, there will be coherent photons, and you can see all the photons are having the same phase. These coherent photons are coming out, getting inside into the active medium through these mirrors. And once you have sufficient number of photons, coherent photons, you will see amplification of light, and finally you are going to get out this laser beam as a output. Okay, so this is a pictorial understanding of these 5 steps and the lasing action. So let us see in detail step by step. So the step 1 is pumping. So the atoms in the atoms or active centers in the medium are in the ground state initially, as shown in figure A, by supplying figure 1A. So this is figure 1A. Okay. So by supplying energy from an external source, the atoms are excited from the ground level to the excited state. So that is what it's saying. So you have many atoms in the ground state. Okay, so to achieve the population inversion fast, we need to send all these atoms to the excited state. To send all these atoms to the excited state, we are supplying energy, and this energy can be in the form of light, so which is called as optical pumping. So we are going to supply energy in the form of light, which is called as optical pumping. So by supplying energy in the form of light, these atoms are going to get excited to the metastable state E2. So all the atoms will be now in the metastable state when we supply photons. Okay, so that means we are going to achieve population inversion. So N2 is greater than N1. So the lifetime of atoms at the excited state is extremely small, of the order of 10 power minus 9 seconds. Therefore, the atoms drop spontaneously from the excited state to the metastable state. Okay, if the atoms are excited directly to the excited state, that is fine. But if the atoms are excited to the normal excited state, suppose there are 3 states. This is N2, this is E2, and this is E3. So if the atoms are excited from the ground state to the higher energy level E3, E3 is a normal excited state. Then the lifetime of the atoms in the normal excited state is very less, 10 power minus 9 second, which is nanosecond. They will drop to this, they will decay through spontaneous emission, they will decay to the energy level E2. So E2 is a metastable state. Then there will be population inversion between E2 and E1, where E2 is metastable state and E1 is the ground state. Okay, so therefore the atoms drop spontaneously from the excited state, normal excited state, to the metastable state. As the lifetime of atoms at the metastable state is comparatively longer. Okay, 1 millisecond, 1 microsecond to 1 millisecond, the atoms go on accumulating at the metastable state. As soon as the number of atoms at the metastable state exceeds the number of atoms in the ground state, the medium goes into the state of population inversion. That is figure B. Okay, so this is figure B. So that is population inversion condition. Okay, so in the first step we supplied energy in the form of light. So all the atoms in the ground state that are excited to the normal excited state E3. Okay, and then because the lifetime of atoms is very less, 1 nanosecond, the atoms in the normal excited state E3, they are dropped down to the metastable state E2. Now the lifetime is more in the metastable state compared to the normal excited state. So now all the atoms are going to accumulate in the metastable state. So the number of atoms in the metastable state is more compared to the atoms in the ground state. So N2 greater than N1 will be achieved. So that is called population inversion. Okay. So the first step is pumping, and once we do the supply energy in the form of optical pumping, and then we see there is a population inversion condition where number of atoms in the excited state are, which is a metastable state, is our number of atoms in the metastable state are more compared to the number of atoms in the ground state, then there will be a population inversion condition. But in case if you have a 3 or 4 energy levels, the atoms, when you have optical pumping, the atoms can excite to the normal excited state E3, energy level E3. Then because lifetime of atoms in the normal excited state is 1 nanosecond, they will decay to the metastable state in 1 nanosecond, and then the atoms will accumulate in the metastable state because the lifetime is more in the metastable state. Then we achieve population inversion between metastable state E2 and ground state E1. Okay, so first step is pumping and second step is population inversion. Okay, so the population inversion is followed by spontaneous emission. So now you have all the atoms are in the, for example, in the metastable state E2, E3 is normal excited state, E and E1 is a ground state. So E1 very small number of atoms, so N2 is greater than N1. Very population inversion is achieved through pumping. Very. So some of the atoms at the metastable state may emit photons spontaneously in various directions. Okay. So now the atoms which are in the metastable state, these any one of the any one of the atom can decay to the ground state through a spontaneous emission. Okay, when the atom is decayed to the ground state through a spontaneous emission, this energy level, metastable energy is more compared to the ground state. So the difference in energy levels E2 minus E1 is emitted as a photon. So the energy of a photon is h nu, which is equal to E2 minus E1, because E2 is higher energy level. So you are going from a higher energy level to lower energy level. So the excess energy is relieved as a photon. Okay, so after achieving this population inversion, any one of the atom in the metastable state is going to emit photons spontaneously. Okay, each spontaneous photon can trigger many stimulated emission along the direction of its propagation. Okay, because once the photon is emitted, we said that this active medium is in between mirrors. So this is 100% reflecting mirror and this is partially reflecting mirror. Okay, once the photon is emitted, this photon is going to get back into the system because there is a mirror. Okay, now this photon, when the photon comes into, now this photon has come back into the system because of the mirror. Now this photon can trigger stimulated emission. We know that to have a stimulated emission, we need to give initial photon that is used as a trigger. Okay, so that stimulated emission can be can occur only when we supply initial photon, and that initial photon will come when you have this spontaneous emission of the atoms. Okay, so as soon as the initial spontaneous photons are moving in different directions, the photons stimulated by them also travel in different directions. Many of such photons leave the medium without reinforcing their strength. The photons emitted in a direction other than the axial direction will pass through the sides of the medium and are lost forever. So if the photons are emitted in sides, some of the photons may last, but many of the photons that are emitted in the axial direction of the system, so then those photons are reflected back into the active medium. These photons are used as stimulated emission and is used for stimulated emission for the stimulated emission. Okay, fine. If the photons are emitted in different directions other than the axial direction, they are lost. Okay, fine. So we understood that first pumping, where we supply energy to the system, and then that is when you have supply the energy to the system, the atoms will go to the normal excited state, and then they can decay to the metastable state. Then you will achieve population inversion condition. Once you have population inversion condition, any one of the atom can decay to the ground state through a spontaneous emission. For the spontaneous emission, you don't need to supply any energy. So atom is going voluntarily decaying to the ground state by emitting a photon, because the difference in energy level E2 minus E1 is emitted as photon. That photon that is emitted in spontaneous emission is used as input photon that can trigger the stimulated emission. It's very important that if you do not have a spontaneous emission, you don't have any photons present in the system, and there will be no stimulated emission, right? If you want to have the stimulated emission, there should be better a spontaneous emission. Okay, fine. So yeah, so that is spontaneous emission. And now in the spontaneous emission, we understood that in spontaneous emission data, there is a photon. There are photons that are emitted when atoms are decayed to the ground state through a spontaneous emission. These photons are used as input photons. Okay, so E1 and E2, let us forget about E3, which is a normal excited state. E2 is a metastable state, for example. Now, so once the photon is emitted in spontaneous emission, that photon is came back as input photon. Why did it come back? Because there are four mirrors. It is the active medium is in between the mirrors, right? So because of these mirrors, they will reflect the photons, and the photon has come back, and this photon is used as the initial photon. So when we supply this initial photon, the atoms which are in the excited state, this photon can trigger the atom to undergo stimulated emission. Once the atom undergoes stimulated emission, atom undergoes stimulated emission, these atoms are going to emit coherent photons. Okay, fine. So once coherent photons, what are coherent photons? As we discussed, coherent photons are nothing but the photons that are having same phase. Okay, so all the photons are going to have same phase, same wavelength, same frequency, right? Yeah. So let us see what the fourth step, amplification. What happened after spontaneous emission? Okay. So a majority of photons traveling along the axis cause stimulated emission and are reflected back on reaching the end mirror. So, as the photons are emitted through spontaneous emission, those photons are um, they are going to cause the stimulated emission because they are reflected back on reaching the end mirror. They travel towards the opposite mirror and on their way stimulate more and more atoms and build up the photon strength as shown in figure D. So this is figure D. So you will see there are more photons that are emitted, and all these photons are coherent photons because these photons are emitted in stimulated emission. The photons that are strike in opposite mirror reflected once back into the medium as shown in figure E. The photons travel once more through the medium, generating more photons and more amplification. So where did this come from? Amplification. How did we get this amplification? We only discussed that whenever there is a spontaneous emission, the photons are feedback, or because of the presence of these mirrors, those photons come back as input photons. These input photons are used to trigger the atoms to undergo stimulated emission. That is why in the stimulated emission, these photons, the coherent photons are emitted. Coherent photons. Coherent photons are the ones that are going to have same frequency or same wavelength, or they are in the same phase. Okay, same wavelength, same frequency, or these photons are in phase. Okay, so in phase means when the two photons are in phase, they undergo constructive interference. Whenever there is a constructive interference is resultant of these two photons. And what happens? Suppose the amplitude of photon 1 is A1 and amplitude of photon 2 is A2. So resultant amplitude is A1 plus A2. So because these are in phase, the amplitude will be doubled, and you will see intensity is directly proportional to amplitude square. Because the amplitude is doubled as these photons are in phase, you will see the enhancement of intensity, that is nothing but the amplification of light. Okay. The photons are then reflected again at the mirror and travel through the medium. As the photons are reflected back and forth between the mirrors, stimulated emission sharply increases and the amplification of light takes place. The mirrors thus provide positive feedback of light into the medium, so that stimulated emission acts are sustained and medium operates as an oscillator. Okay, so now we understood that after spontaneous emission, the photons that are emitted are used to trigger the atoms to undergo stimulated emission. Once there is a beginning of stimulated emission, then there will be emission, there will be coherent photons that will be emitted. These coherent photons are in phase and they will undergo constructive interference, and hence amplitude will be doubled and intensity will be increasing. That is what is called amplification of light. And because of the presence of these mirrors, we are going to get this amplification of light, and hence the optical resonator or optical cavity provide us the positive feedback of the photons into the medium, and so that stimulated emission acts are sustained and medium operates as an oscillator. Okay, so the fifth step is oscillations. At each reflection at the front end mirror, light is partially transmitted through it. The transmitted component constitutes a loss of energy from the resonator. When the losses at the mirrors and within the medium balance the gain, a steady and strong laser beam will emerge from the front end mirror. Because we have backside, we have 100% reflecting mirror, but front side of the active medium, this is active medium, we have partially reflecting mirror. So this one is connected to a pump. Okay, so whenever photons are emitted through stimulated emission, some of the photons may uh, lost we may lose some of the photons because this is partially reflecting mirror. But here there is no loss because it is 100% of mirror, 100% reflecting mirror. Because of this loss of energy from the front end mirror, if we gain the amount of energy that we lost from the front end mirror, then we are going to get sufficient energy for the laser to beam to come out as a output from the front end mirror. So these are the 5 steps that occur in a laser system where we are going to get laser beam as outputs. What are the 5 steps? To devise again, the first step is pumping. Pumping is very important because if you do not have a pumping, all you are going to have atoms in the ground state. Through pumping only, we are going to send them to the excited state or metastable state E2. Okay, once we do pumping, supply the energy. Pumping is nothing but supplying energy to the system. Okay, once we supply the energy to the system, then we are going to achieve population inversion. So the second step is population inversion. The third step, once we have population inversion, there can be a spontaneous emission where atoms are going to decay to the ground state spontaneously by emitting a photon. So there will be a spontaneous emission. Once you have spontaneous emission, then this photon, for example, is going to come back as an input photon because there is a mirror here and mirror here. This input photon can trigger the atom to undergo stimulated emission. Okay, so when you have the stimulated emission, that is going to emit coherent photons. So these coherent photons are in phase and they are undergoing constructive interference, and there will be a amplification of light. Once you have amplification of light, there can be a loss of energy, loss of photons from the front end mirror. But when we give the same energy in the system again, we will see light is emitted. as a laser beam. So there is oscillations, I mean loss or gain. So the last step is a oscillations, pumping, population inversion, spontaneous emission, amplification, and oscillations. At the end of these 5 steps, we are going to see the laser beam as. So this total process is called as lasing action. Okay, to achieve this lasing action, we need optical resonator that is connected to a pump. And optical resonator is nothing but two mirrors. One of them is 100% reflecting mirror, and one of them is partially reflecting mirror. In between these two mirrors, you have an active medium. Active medium is nothing but the host material plus active centers. Active centers are nothing but the impurity atoms. Once you have impurity atoms, they will provide us metastable state. Okay, metastable state is important because with that only we can achieve population inversion, because the lifetime is more. Okay, yeah. So now we understood the lasing action where all these 5 steps occur. At the end, we are going to get laser beam as output. Okay, let us just revise some of the questions what we understood through discussion of these. So why do we need population inversion? We need population inversion to initiate the stimulated emission that emit the coherent photons. Very good. So how do we get population inversion? We use pumping techniques and metastable state to achieve population. Only pumping technique is not sufficient, not enough to achieve population inversion, but we need also metastable state that will help us to achieve the population inversion. What is metastable state and why do we need it? Metastable state is a non-equilibrium state where the lifetime of atom is longer compared to the ordinary excited state. And how long? Long is 1 10 power 3 to 10 power 6 times more compared to the normal or ordinary excited state. And also we have discussed about lasing action. Lasing action we have discussed 5 steps, right? So next we are going to discuss about different types of lasers. So how many types of lasers that we can have? Okay, so lasers are divided into different types basing on different considerations. We divide them here on the basis of materials used. Based on what kind of material you are going to use to construct or fabricate a laser, based on the material that you are using, we are going to divide these lasers into different types. For example, solid state lasers, where you have ruby laser, neodymium IARE laser, are few examples. And gas lasers, where you are going to use gases to fabricate these lasers. Solid state lasers, you are going to use solid materials. Gas lasers, helium neon laser, carbon dioxide laser, right? And the third category is semiconductor diode lasers, where you are going to use semiconductor materials, gallium arsenide laser, indium phosphide lasers are few examples. Based on the material that we are going to use to fabricate the laser, we are classifying the lasers into 3 categories here: solid state lasers, gas lasers, and semiconductor diode lasers. Most of these lasers emit light in the red or infrared regions. Most of these lasers emit light in the red or infrared regions. Lasers work in continuous mode or in a pulsed mode. So the output beam that we are going to get, that can be a continuous beam or it can be a pulsed beam. Pulsed, it's not a beam, so it pulsed laser. So you will get one laser pulse, and after some time delay there can be another laser pulse, so that is called as pulsed mode. So you can have the laser output as a continuous laser beam, or you can have a pulsed laser output. Okay, so this is just the classification of lasers based on what kind of materials we are going to use to fabricate the material. So in the next presentation, I think I'm going to discuss about different types of laser. For example, in solid state laser, we are going to discuss about ruby laser, and in the gas laser, we are going to discuss about helium neon laser. So that I will continue in the next presentation. Okay, that I will continue in the next presentation. So this, yeah, thank you.
Like, share and subscribe. Hit the bell icon for more updates.